So, well, hello everyone at home. Welcome to another Wednesday evening at Cambridge University Astronomy. I'm here today with the CAA, the amateur astronomers, who have told me that the skies are looking about halfway clear. So fingers crossed we should get to do some stargazing starting around 8 o'clock or so. But before that, I'm very happy to introduce our headline speaker. I'm here with Dr. Hayley Macpherson from who's a postdoc and in the maths department. And she's going to tell us about how to build a universe. So over to you, Hayley.
Awesome. Thanks so much, Matt. Let me just share my screen. Okay, so it's really awesome to be here. I really wish that the circumstances were a bit different and we could be in person, but we make do with what we've got. So yeah, as Matt said, I'm going to talk to you today about how to build a universe. So specifically in cosmology, how we study large-scale structure using simulations. And so the first thing I'm going to do is explain exactly what I mean by cosmology and large-scale structure. And eventually I'll get to what I mean by simulation in this context as well. So starting with cosmology, and we've had quite a few great talks recently on cosmology in this series. So I'm sure you're all experts by now, but just in case, there are two main definitions of cosmology, which you might hear. The first is that cosmology is studying the universe as a whole, rather than studying its contents like stars, planets, and galaxies. So looking at questions like, how did the universe begin? How will the universe end? And what happened in between, rather than say, how do stars evolve? The second definition, which I like better and I think is more accurate, since many cosmologists do study things like galaxies themselves, is that cosmology is more the study of the largest scales in the universe, in both space and in time. So when I say large timescales, I mean billions of years. So we're really capturing the entire history of the universe over these timescales. And when I say large spatial scales, I mean billions of light years, which is the distance that light travels in 1 year, which is about 9,000 billion kilometers. And one thing that cosmologists really love to study is the large-scale structure. And to explain exactly what I mean by this, let's take a look at some observations. So this picture here is a map of the local universe. So you can imagine Earth sitting at the center of this diagram, not to scale, obviously. And as we move around the edges of the circle, we're looking in a different direction on the sky. And as we move further out in the circle, we're looking further away, with the edge here being just over 1 billion light years away. And each of these points is an individual galaxy. So we observed each of these galaxies and just mapped their position on the sky in this diagram. And so this picture shows us how galaxies are distributed in the local universe. And one thing you probably notice is that they're not quite smoothly distributed. We have some regions that have fewer galaxies, they're underdense, and we call these voids. And some other regions are quite dense, where galaxies have clustered together, and no surprises, we call these clusters. There are also these kind of elongated type structures that connect clusters to one another, and these are called filaments. And so when a cosmologist says the large-scale structure, they're referring to this spiderweb type structure of voids, filaments, and clusters of galaxies when we look at the universe on really large scales. And as we just saw, we can measure what this structure looks like by observing galaxies and mapping their position on the sky. And the way that these galaxies are clustered, so for example, how far away these clusters are from one another or how dense they are, can give us clues about what the universe is made of. And as well as measuring the galaxies' positions, we can also measure how fast they are moving away from us to see how space is expanding. So one of the first measurements of this expansion was by this dude, Edwin Hubble, in 1929. And this is a very, very famous plot of his, which shows his measurements of distances and velocities of extragalactic nebula. So each point on this diagram shows the velocity and distance of a different nebula. So these ones down here are both closer to us and moving away from us slower. And these ones up here are both further away and moving away from us faster. And we can see that Hubble has fit a kind of straight line to these points. And this straight line is exactly the proof that our universe is expanding. So lots of people did predict this theoretically, but Hubble was one of the first people to actually show this with observations. But one thing you might ask is, how do we choose this line? How do we know what to expect? How steep should this line be? And what does the gradient of that line tell us about the universe? So what we need is a mathematical model to tell us how the universe should expand. So a model that can give us the equation of this line that we can then compare to our observations. And a good place to start is with general relativity. So this is the best description of gravity that we currently have. So it seems like a good model to use for our universe. But unfortunately for us, the equations of general relativity are very difficult to solve. And in some cases, it's actually impossible to solve these equations by hand. So these are the famous field equations here, and you might think they look quite simple, right? Trust me, they're not. So this is just a quick look into what these equations actually look like when you expand out each one of these terms. And trust me, this is just the beginning. So what we do in most areas of physics, and definitely in cosmology, is we simplify them. So we make some assumptions that make the equations much easier to solve. And so specifically, if we go back to our diagram of the local universe, we notice that it's lumpy. The distribution of galaxies is not quite uniform. So this makes things really hard mathematically. So what if we just assumed that it wasn't lumpy? Let's assume that the distribution of matter in the universe is perfectly smooth. So this makes our equations a lot easier to solve. So this is an oversimplification of the assumption that we actually make, but even still, you might think it's a bit of a crude assumption, but it's actually pretty reasonable. And I'm going to make an equally crude analogy. If we look at the open ocean on small scales, we notice that we have a lot of structure. We've got waves breaking and not breaking, going all directions and interfering with one another, and it's basically just a mess. But if we zoom out and look on larger scales, it looks pretty smooth. So while, yes, we're ignoring a lot by assuming it's smooth, it seems to make sense so long as we look on large enough scales. And as expected, this makes our equations much easier to solve. So easy, in fact, that we can actually do it by hand. And this is a really common undergraduate exercise. And usually in your first cosmology course, you'll be solving Einstein's equations for a perfectly smooth universe and looking at how it expands over time. So now we've got some equations for the line on Hubble's plot. So now what we need are some observations to compare it to. And since Hubble, our observations have improved a lot, and there are lots of different ways that we measure the expansion of the universe. But I'm just going to talk about one of those, which is supernova type 1a. So a supernova just means a star exploding, and the type 1a just refers to a particular type of supernova. So these are very, very bright events, as we can see from this picture, but this is a supernova outshining its host galaxy. So this here is a galaxy, of course, containing millions of stars, and this is a single star exploding. So these are extremely violent events in the universe. And actually, the way that the brightness of these stars, or these exploding stars, changes over time as they explode is very predictable. It's almost always the same. And what this means is that these objects are really useful to measure distances, because we can attribute any differences in this light curve to how far away the supernova is from us. So let's look at some observations of supernova type 1a. So this plot here, each one of these points is a measurement of an individual supernova. And so we've got way, way more than this now. This is quite an old plot, but you'll see why I'm showing you this one in particular in a little bit. So here we're looking at the brightness of these objects versus their distance from us, but you can still just pretty much think of this plot as an improvement on Hubble's earlier diagram. So these objects down here are both closer to us and also brighter. And these ones over here are both further away and also fainter. Makes sense, right? And so based on the simple model, our simple smooth universe model, this is the line that we expected the data to match. So this one down the bottom here. And when we looked a little bit further away, we noticed, and you might be able to see here, that these few supernova are slightly above the line. So it's pretty hard to see. It's a pretty tiny difference. So let's zoom in. And rather than the brightness, what we're going to look at is the relative brightness with respect to this center dashed line here. So we've just zoomed in now. This is the same plot. And so this line down here is the one we expected to match our observations. And so here you can more easily see that these further away objects are definitely fainter than we expected based on this model here. And so this can imply that maybe these further away supernova don't actually have this constant brightness that we thought, and maybe these more distant ones are just intrinsically different. But lots and lots of research has been done to show that that's probably not the case. So the other option is that these objects are further away than we expected them to be, and which in turn means that space is expanding faster than we thought it was. And not only that, it's accelerating as well. So we'll notice that this top line here clearly fits this data a bit better. And it actually fits the data so much better that it earned the authors of this paper a Nobel Prize, shared with some other people. And so this slightly better fitting line tells us what our universe is made of. So this is because the way the universe evolves over time, and therefore how it expands, is quite heavily dependent on what it's made of. So just like, for example, water will flow differently to, say, honey, a similar effect will make the universe behave differently depending on what it's made of. So this pie chart here shows us the breakdown of the contents of the universe today, as inferred from observations like these. And we can see the majority of it is dark energy, 70% or so. So we don't know what this is, so I'm not going to talk about it too much. But what we do know is that it's the driving force behind the accelerated expansion rate that we observe. The rest of it is in matter. Most of that is in something called dark matter. So only about 4% of the universe is made up of atoms, which is literally everything that you can see. So the sun, the earth, you, your house, galaxies are all only 4% of the universe. And we also don't really know what dark matter is. I'm not going to go into much detail, but basically this is some kind of matter that is different to the matter we're used to, and we can't see it, hence dark, but we know it's there because of its gravitational effects. And so all of this information about what the universe is made of came from us using our simplified model, where we assume that the universe was smooth. But of course, we know from the mere existence of you and me and the Earth and galaxies that it's not really. So the fact that the universe is not perfectly smooth is exactly the reason that galaxies formed, and it's exactly the reason that you exist. So it's something that we do need to care about at some point. So to get here, we used Einstein's equations with some simplifications. And as I said earlier, these simplifications are valid so long as we look on large enough scales. But as I also said, we do care about what's going on small scales because this is also important. And if we want to look on these smaller scales, say on the scale of a galaxy or a cluster of galaxies, which is a small scale to a cosmologist, we definitely can't assume the universe is smooth. But as we saw, I showed you briefly, Einstein's equations are very complicated. And they're actually impossible to solve by hand for the kind of complex structure that we see in the universe. So what we need is some equations that capture the complex structure of the universe, but are also easier to solve. And we're lucky in that sense because we have Newtonian gravity. So this is Newton on the left-hand side. And Newtonian gravity provides a pretty good approximation for general relativity under certain circumstances. So like describing motion here on Earth. So if you throw a ball in the air, say, Newton's equations will tell you pretty accurately where it will fall. It's also okay in the solar system so long as we're not too close to the sun. So maybe it's okay for cosmology too. But while Einstein's equations are much simpler than Einstein's, they're still pretty hard if we want to include the kind of detail that we see in the universe. So we use computers to solve them. And specifically, we use simulations. So these are just something that uses a computer to imitate a process or a system. And I'm sure most of us are familiar with interactive simulations, for example, video and computer games. So in these simulations, the game player decides what happens next. And while some of these simulations will incorporate some physics, so when you jump up, you'll generally fall back down, largely you still control what's going on. And these kind of simulations imitate things like life, adventure, fighting, and farming. And so we also use simulations in physics, where instead we imitate a natural system or a process. So instead of a farm, we imitate a natural system or a process. And these are used across most areas of science, like chemistry, sociology, biology, weather, and of course, astrophysics. But in these simulations, the laws of physics decide what happens next, rather than the game player. And so while our observations are really, really useful, we can't do much with them without having something to compare them to. And also our simplified smooth universe model is okay for a lot of things. It doesn't quite do the job on its own. So we need more complex models. And for these, we need the help of a computer because the equations are quite tricky. And also, as we can see from this diagram here, we have much fewer points when we look further away. So this is because it's much harder to observe things when they're really, really far away. So for example, if we look at some images of nearby galaxies, whereby nearby, I mean up to only a few million light years away, we can see these amazing detailed structures. We can see spiral arms and even maybe resolve individual stars and clusters of stars in these galaxies. But when we look at more distant galaxies, they're really not quite as pretty. So these ones are many billions of light years away and some of the most distant galaxies we've ever seen. So instead of being these beautiful structures, they kind of become these like blobby looking things. And if I told you that this was a galaxy, you probably wouldn't believe me straight away. So this means it's really hard to observe what the universe was like really far away or a really long time ago. And so this is where simulations come in. So we can run a simulation and compare it to the more nearby stuff that we can see really well. And if it matches, then we can use the same simulation to infer things about the stuff that it's harder to see. But just as in any computer game, we need to start somewhere. So where and how do we even start these simulations? Luckily, we've got a pretty good idea of what the universe was like near its beginning. So this is the cosmic microwave background radiation, or the CMB. I'm sure you've heard of it in some of our previous talks. This is a map of the two-dimensional sphere on the sky surrounding us, and we map it onto this shape in exactly the same way that we map the surface of the Earth onto this same kind of map. So this is a map of the temperature of the first light that was able to freely travel through the universe, and it's the furthest back in time that we'll ever be able to see using light. It's a picture that tells us what the universe was like when it was only 300,000 years old, and that's young, trust me. As we measure this radiation today, it's traveled through the entire history of the universe, and it tells us a lot about the universe was like in its early days. So what we generally do is we use the CMB to start our cosmological simulations. So we set up initial conditions that look like the CMB, and then we can run our simulations using several slightly different theoretical models. And each of these have slightly different sets of equations, and therefore we will get slightly different looking universes out at the end of the simulation, of each simulation. And we can then compare each of these to our observations and see which one fits best. And then we know which of these models is the best model to describe our universe, and we can therefore use this model to predict things about parts or times in the universe that we can't observe. So this is the basic structure of most cosmological simulations, but I just wanted to go into detail about some of the best ones that we have at the moment. So I'm going to tell you about this picture here, which I've been showing you for my entire talk, but haven't mentioned at all. So this is a snapshot from one of the illustrious simulations. So these really are some of the most accurate models of our universe that we have at the moment. And I just want to tell you and emphasize, tell you a bit about the level of detail in these simulations and all of the physical processes that they take into account. So even just looking at this picture, you can probably already tell that this is a really, really complex simulation. But just to name a few things, they include the huge clusters of dark matter. So this purple kind of web structure, this forms the main large-scale structure in the universe, alongside normal matter like gas and stars and dust, as well as chemical processes in this gas, black holes and radiation, so the way that light travels through this structure, magnetic fields, individual stellar evolution, including the death of these stars in supernova and how the result of that supernova feeds back elements into further structure formation. It's really amazing. And here is a movie of one of these simulations. So down the bottom left here, when I move my cursor, you can see how much time has elapsed since the Big Bang. On the left-hand side, we're looking at the dark matter distribution. So this makes up the majority of matter in the universe. And so its gravitational interactions define the shape of the large-scale structure of the cosmic web. Lighter regions have more dark matter, darker regions have less. On the right-hand side, we're looking at the gas temperature. So that's what's going on the normal matter side of things. So galaxies, star formation, gas, winds, all the complex stuff. And the red regions here are hotter and the blue regions are cooler. So once structures collapse enough to form stars, we see a bunch of wild stuff going on. And these explosion type things that you're seeing are from active galactic nuclei, or AGN. So these are jets caused by accreting mass onto the supermassive black hole at the center of galaxies. And so this movie should hopefully give you an idea of just how complex these simulations really are. And there are a lot of people here at Cambridge in the IOA who are working on these simulations in particular, led by Deborah Siaki. So as you might imagine, these kind of simulations require some pretty serious computing power. So this picture here is an example of a supercomputing facility. So you can think of it as each of these little cells in each of these, behind each of these windows as an individual computer, and they're all working together to create one giant, powerful supercomputer. And just to put into perspective the scale of these things, your smartphone, for example, is capable of 100 million operations per second, which already sounds insane. But if we go up to your typical desktop computer, this is capable of about 10 billion operations per second. And now, one of these typical supercomputing facilities, and keep in mind that these do vary in size quite a lot, are capable of up to about 10 quadrillion operations per second. And personally, I didn't even know what the word quadrillion meant until I made this slide. So some of these simulations run on a large portion of these computers for a very long time, sometimes weeks or even months. And so that is a lot of computing power. And I'm emphasizing a lot how incredibly impressive these simulations are, because that's true, but we've still made quite a lot of simplifying assumptions to get here. So for example, the smooth universe assumption is still in here in a way. And we've used Newtonian gravity when we know that Einstein's theory should be more accurate on large scales. And these assumptions are probably safe, but not all of them have been thoroughly tested. And so it's really important to make sure that these assumptions that go into our research are actually okay. Some people believe that some of these simplifying assumptions could be the reason that we think dark energy and dark matter exist, and that these could actually be just our assumptions tricking us into thinking that these things are there. So luckily, there is lots of really exciting research going on right now to try and see if our assumptions are okay. For example, and I'm a bit biased here, but I'm going to briefly tell you about one assumption that I'm working on testing. So I mentioned before that we swapped to Newtonian gravity for these big simulations because the equations were quite a lot easier to solve. And I also said that Newtonian gravity is basically okay on small scales, like on Earth and most of the solar system. Which is true, but when we use it on larger scales, like those who are interested in cosmology, this is not necessarily the case. And there are a few reasons for this, but one reason that there could be some differences is that in Newtonian gravity, light travels at an infinite speed. So it's based on instantaneous action at a distance. So this would mean you could call up your mate on the other side of the galaxy, or even the other side of the universe, and be connected instantly. However, in Einstein's theory, light instead travels at a constant finite speed, which means that it takes time to travel any distance at all. And so there'd be quite a bit of lag in connecting across the galaxy. But if we think closer to home on small scales, this also means that there is a slight delay when we look at anything. For example, the light emitted from your computer screen right now does actually take time to reach your eyes. So you're really looking at your screen how it was about a nanosecond ago. And this difference is obviously not very important or noticeable at all. But if we move to slightly larger scales, though still tiny scales in a cosmologist's eyes, this can have quite a noticeable effect. So on the scale of the Earth, it only takes light about 60 milliseconds to travel from one side of the Earth to the other. And this may also seem like a really short amount of time, but actually this distance here also, starts to become important. If we ignored this 60 millisecond difference, GPS wouldn't work at all. So the little blue dot, which tells you where you are on your map, could be off by up to 11 kilometers if we didn't consider this 60 millisecond difference. And of course, if we increase the scales even more, this difference can become even more noticeable. So it takes light about 8 minutes to travel from the sun to here on Earth. So if the sun were to just spontaneously disappear for whatever reason, we wouldn't have any idea for about 8 whole minutes. But on these scales, we know that Newton's theory is still mainly okay for most things. But in cosmology, where our distances are way larger, so light takes millions of years to travel between galaxies and billions of years to cross the large-scale structure. In Newton's theory, there is no delay here. And this instantaneous action not only applies to light travel between galaxies, but also to gravity. So galaxies feel the gravity of other galaxies instantly, whereas in Einstein's theory, there's a delay between this too. And so I do want to just make clear that even Einstein's theory hasn't been properly tested on cosmological scales, but there are many situations that we know of when Newton's theory just doesn't cut it. So it makes sense to question this. And these state-of-the-art simulations, as I told you, use Newtonian gravity because it's a bit simpler. So the question is, if we do these kind of simulations using Einstein's full theory instead, do things look any different? And this is something that has only been feasible for the past 10 years or so, and even less, because our computers just weren't powerful enough to do these kinds of calculations, nor did the numerical methods even exist much earlier than that. So this is a really exciting new field, and of course I'm biased because it's my field, but this is already starting to give us hints that things might not quite be the way they seem when we use general relativity to look at the universe. So that's it. Thank you very much.
Wonderful. Thank you so much, Hayley. Sorry, I was scrambling for the unmute button. Yes, okay. Virtual round of applause for Hayley. So yes, like I said, any questions, pop them in the YouTube chat. I guess I have one question to kick us off while people think. You spoke a little bit about dark energy. Obviously, that's one of like the biggest mysteries that we have in cosmology at the moment.
Yeah.
Like, what would your bet for what's, if you had to bet, what would you guess dark energy was? Because I know there was some results in the newspapers a few days ago that found some kind of exciting hints about dark energy. I just want to get your thoughts on what you think dark energy might be.
Yeah, I didn't see those exciting new results. I'm not really up to date on that, on the latest stuff, but I have absolutely no idea what it actually is. So I don't really want to make any bets, but there is a particular idea that I like the best as the nicest, even though it doesn't seem like it's very likely. And this is, of course, again, related to my research. So there are some people who have done simplified studies, like mathematical studies, where if you consider general relativity in full without making any kind of simplifying assumptions like we do, then you can actually explain many of our observations without introducing dark energy at all. So this is something that's really interesting. And I personally really, really like the idea that this crazy fluid that fills our universe and contains 70% of the energy density is actually just general relativity. Like, I think that's a really nice explanation, although there are a few studies that show that it's unlikely that that is actually the explanation, although that's my favorite.
Great, thank you. So a question that's come in from Gaurav wants to know that can gravitational waves travel faster than the speed of light?
That's a really good question. So in regular general relativity, they travel at the same speed. So this is a really useful test of general relativity that we've been able to do with measurements of gravitational waves. So especially, we can actually only do this test for mergers of neutron stars when we have both an observation of the light emitted and also of the gravitational waves, because then we can measure the delay in receiving both of these signals. So we measure the light from the merger of the two neutron stars, and we also measure the gravitational waves from the merger of the neutron stars. And if they arrive at about the same time, then we can say, okay, they're traveling at the same speed. And so this, from the first merger of two neutron stars that was measured by LIGO, the difference between the two was totally negligible. It was like, can't remember the exact number, but it was less than 1 in a trillion or something like that. So they travel at very, very close to the same speed as we've measured. But there are some theories of, say, modified gravity in which gravitational waves do travel at a different speed. So we need way more objects to be able to say with more certainty, but these are good tests of things like modified gravity.
Awesome, thank you. A question from Julia wants to know where the fastest supercomputers are.
Oh, that's a really good question. There is a list online, but I'm completely blanking of what it's called. I'll post it in the YouTube chat afterwards. But I think maybe it's like the top 50 supercomputers in the world, and I want to say one of the top ones is definitely in Switzerland, in Geneva, I think. I could be completely wrong on this. I'm going to stop talking and stop saying more and just say I'm going to look up the website after this and post it in the YouTube comments. So stay tuned.
Thank you. And a question from Julian wants to know: do we understand why galaxy strands form?
Oh, why the filaments form?
Oh, yeah, I guess that means the filaments in the
Yeah. So these kind of these things. Okay, why they form? So I have absolutely no idea. I don't really know if there's a good explanation for why we get this particular kind of like cosmic web structure. Yeah, I have no idea. That's a really good question. Sorry.
No, I mean, yeah, it's always a very good question if the speaker is stumped, right?
Yeah, totally. I'd never thought of that. I will now.
Cool. Well, thank you guys so much for the questions. Thank you again, Hayley, for that super enlightening talk. That was wonderful. Now I am crossing my fingers very hard and seeing how things are looking in the sky. If we go over to our amateur astronomers in the CAA, how are things looking over there, guys?
Definitely nothing to see here. It's cloudy with one star.
I see some thumbs down. What about where you are, Paul? Thumbs up. Okay. Okay, at least one person has some clear skies. Well, in that case, so thank you again, Hayley, and I will hand over to our observers to do what stargazing we can. So over to you, Brian.
Okay, thank you very much. Well, last week we had trouble with condensation getting in the cameras, and we got some very poor images, but we're suffering from condensation a bit higher up now. Is David, is your sky clear?
Yes, I can see bits of Messier 33 at the moment.
Oh, good. Okay, so we'll go for it. And we'll start off at the moon. And here we've got a crater known as Aristarchus.
This one's actually Copernicus.
Oh, that's a good start, isn't it?
Sorry.
No, swivel over to...
You want? I thought we'd go and try and find Aristarchus.
All right, yeah, we'll start off with Copernicus. Right.
But you might have to direct me.
Okay.
And everything's upside down and backwards just to make it easy.
Oh, thanks. Okay, the moon is virtually full. And when the moon is full, you don't see any shadows. So you can't see that that's a crater very well. You can just see the light patch. But what does happen at the full moon is you can see the ejecta, the stuff that has been splashed out during the impact. And Copernicus is a comparatively young crater, and the ejecta is quite well seen. Right. And that, to give you a scale, the crater is about 80 kilometers or 50 miles. And you can see it's a fairly even ejecta pattern. But if we go towards Kepler, which is further to the west, here we see it coming in. It's just coming in now and it's heading towards the middle. And this is a smaller crater, but you can see the ejecta pattern seems to radiate round three sides. So the meteorite or small asteroid that came in to form this crater came in at a very low angle from the left-hand side of the screen, and it made the crater, but the crater is still round. No matter what angle the asteroid hits the moon, it will always make a round crater, except if it comes in at a very, very low angle, maybe 1 or 2 degrees. And there are a couple of oval craters on the moon. We'll look at them when the moon is in the first quarter. But this one, it just shows it came in at about 15 degrees and stuff's radiated away from the direction of travel. Now we'll head towards Arcturus.
So which way do you want me to go? Do you want me to go further
Northeast.
Northeast?
No, northwest, sorry.
Northwest.
Sorry.
Well, okay, so this is west.
Yeah, and then you go down, you bring it, that's it, and then go, it should be below Kepler.
Now I want to go down, so I'm going to press up.
Yeah, everything, I'm frantically trying to, here it comes.
There we go, look at that.
Yeah. Right. Now, the Arcturus crater, Aristarchus crater is very bright because it's very young. It's probably only a few 100 million years old. So the ejecta around Aristarchus is very bright. And the reason I wanted to look at this, because usually a couple of days after a full moon, which it is now, sometimes it appears electric blue. And this blue colour is due to titanium oxide in the crater. And it only happens, you only see this lovely blue colour for a few short hours each month, because it's dependent on the sun being at the right angle and shining down on this crater and just catching the light so it appears blue. But unfortunately, I think we've missed it, as it's not showing any colour.
No, I'm not getting any colour today.
No, but beneath it, you can see it's in a rough square. And that square is about 200 kilometers each side and is called the Arcturus Plateau. That's it, going the grey bit. And then if you bring your cursor down, you can see the square, and then go to that's the one corner. Aristarchus, sorry, is the other corner, and then go to the right. That's it, and then down. So roughly that is just on a 200-mile square, and that is the Aristarchus Plateau, and it's a fairly recent volcanic area. Most of the volcanic activity took place on the moon between 3 and 4 billion years ago, whereas that plateau is about 1 billion years old. So you can see it's comparatively young, and it was one of the last areas on the moon that was volcanically active. And it's raised up, especially around the Aristarchus crater, about 2 kilometers above the level of the ocean of storms, which it sits in, that sea, the grey area all around it. So this is the last sort of bits of volcanism we see. It's not so much a volcano as a large amount of lava that was thrown up. Last week we did have a go at looking at a volcano, but they're so very small, they're on the limits of our telescope's ability. And this this isn't as sharp as it could be because the moon is very low down. It's near the horizon. So we're looking near through a lot of atmosphere. But just beneath the crater, you can see another little light patch. And that's and a sort of tadpole effect. That's it. That's Schroeter's Valley. And where you had your cursor was a vent, a volcanic vent, and then it trails off in a wandering line to up and to the right. Yeah, and that is a collapsed lava tube. It's nearly getting on for a couple of 100 kilometers long, this lava tube. It's only about 1 kilometer wide, so it's very difficult to see. But the lava tube emptied of lava, and then the roof has collapsed. And so we see it as a sinuous rill. And this is the largest rill on the moon. So it does show that there has been a lot of volcanic activity. Okay, now we can't move over to Mick, so we'll go over to David in Halton and see what he's found.
What do you want me to go for next, Brian?
Either the Pac-Man or 891.
Right, I'll try 891.
Whichever's clearest.
Yeah.
Okay.
I do have some moon videos if that's any help, Brian.
Okay. Well, we'll see how we go. Right.
Right. I've been. Can you see my screen?
Yes, we can see your screen.
Jolly good. Let me get rid of a few bits and pieces. I've got 2 cameras running. This is a color camera, and as Messier 33 dives in and out of the clouds, we could just see it here.
Right, we can see some of the spiral structure.
And there's a faint blue hint of the spiral arms. The other camera is this one, and this was a shot captured maybe 5 minutes ago in a gap in the clouds, and you can see it here.
Yeah, we can see the spiral structure.
See the structure there, and it's been quite interesting to watch this dodge in and out of the clouds.
Actually, as you move the screen, we can see the structure a little better. Yes,
there it is.
We can see it spiral in amongst the muck that's up there. There's a lot of high level cloud, and that there is a gas cloud in Messier 33.
Yeah.
In our local group, there are about 30 galaxies. Most of them are small, but there are 3 spiral galaxies. The Andromeda Galaxy, which is the largest, then the Milky Way, and then the Triangulum Galaxy, or Messier 33, and is the smallest. And it doesn't have much of a nucleus. If you show where the nucleus is, that it's not very well lit. Whereas the Andromeda Galaxy and the Milky Way Galaxy has a huge central bulge where there's a huge quantity of stars. But this galaxy is about 60% the size of our Milky Way, but only contains 10% of the stars. So it's a very feeble galaxy with no central bulge. And the Milky Way and Andromeda both have supermassive black holes at the center of the nucleus. It's a feeble nucleus. It does have a black hole, but it's only about 3,000 solar masses, so it's way too small to be a supermassive black hole. So that's a very poor nucleus in this galaxy, and the galaxy is it's also associated with the Andromeda galaxy. They're gravitationally bound, and the Andromeda galaxy and our galaxy will eventually collide in about 5 billion years. And of course, the Andromeda will bring, oh yes, that's coming along nicely now. You must have a clear bit of sky now.
Yeah.
That's coming along a treat.
Mars
We
is
can
looking very bright.
see the structure much better now. And the Triangulum galaxy will orbit around the two galaxies that have merged and may eventually join the train wreck. But that's in billions of years' time. But if we go back to that gas cloud, which we can see down the bottom corner there, that is like our Orion Nebula that we can see in the winter sky below the belt of Orion. And it's actually a huge gas cloud compared to our Orion Nebula. The Orion Nebula is a modest 25 light years across, but this is 60 times bigger than the Orion Nebula. So that's why we can see it at this huge distance. We're looking at about 2.75 million light years away. So to see this gas cloud is quite amazing, and it just shows how big it is. And there's a cluster of stars that are illuminating it so we can see it. So that's the Triangulum galaxy, our smaller brother, though they have found one black hole in it, a stellar black hole. It's the largest stellar black hole known. I don't know where it is in relation to this picture, but it's nearly 16 solar masses, because normally stellar black holes are sort of 5 to 10 solar masses, but this one's a monster one, and it's orbiting a monster star. That's how we know it's there. It's been picked up in X-rays because the star at about 70 solar masses is depositing stuff onto the accretion disk of the black hole. And that's how we pick it up. Where the stuff strikes the black hole, it gives off X-rays, so we can pick it up. And this black hole has a rather dull name of just X7. Okay, so we'll go back to Paul, and he should have picked up his galaxy if it's in a gap in the cloud. Are you there, Paul? Apparently not. He's probably still struggling. Oh, he's on mute. Well, David, if you carry on and go to your other object.
Sorry,
Right.
I was talking to you while I was on mute there, wasn't
Yeah,
I?
yeah, I know.
You stay with Paul, and I'll go for M52.
Okay. I think this is the right field of view.
But you've got some cloud across it.
But I can't actually see much by the way of galaxy. I think it's here. But let's
give it.
Yeah.
The trouble is, if you give it a longer exposure, the sky will get lighter because of the moisture in it, won't it?
Yeah.
Yeah. So. Is that cloud or you? No, here we come.
Me.
Yeah.
Just playing with the settings.
trying to get it.
Trying to see if I can see anything. But it's you can see the countdown going on here. I
Yeah.
got 1 minute 22 seconds before I'm going to get a nice long exposure.
Oh well, we'll just hang on.
So talk amongst yourselves.
What we're hoping to see is another spiral galaxy that's edge on. So imagine a galaxy as two fried eggs back to back, and the yolks are the central bulge, and the whites of the eggs are the spiral arms containing millions of stars. And because the galaxy is edge on, we'll see or hope to see the amount of obscuring material there is when you look edgeways onto a galaxy. How long have we got to go before it comes?
32.
32 seconds. Oh, right. And this galaxy looks very much like our own Milky Way does in the southern sky, and it was often considered the twin of the Milky Way galaxy. But recent studies have shown that it's very different, and that instead there's dusty lanes being blown at. What's happened?
Don't worry, that was the image arriving.
Yeah, okay. I thought it got totally fogged things. That's
One or two dust bunnies.
yes.
No sign of any galaxies though.
No, I can't see any. No.
Okay, you might want to go over to David, and I'll persist trying to make sure I'm on target.
Okay, I'll come back to you then.
Yeah, this might be it here,
Right.
but that might not be.
Yeah. Good. Okay. Well, we'll go back to David and see how he's getting on with an open cluster, an open star cluster, which will hopefully be brighter and be able to be seen through the high cloud.
Yeah, I think it's the cloud that's doing for me.
Yeah.
There's a ring round the moon now.
Oh, right. That wasn't there earlier.
No.
Okay. Oh, well done. Right. This is an open cluster, and it's called Messier 52. And it's Messier was a French astronomer who looked for comets, but he kept coming across faint fuzzy patches in the night sky that kept fooling him. So he made a list of 100 objects that weren't comets, and that's why we keep calling certain objects Messier objects. And this is a nice open cluster in Perseus, and there are many clusters around the Perseus and Cassiopeia region. So it's often worth sweeping that region with a pair of binoculars so you can see the clusters that there are. This is a nice open cluster. It's a relatively young one. It's only 35 million years old, with a couple of hundred stars in it. And it's in between the two spiral arms. We live in the Orion spiral arm, and most of the other clusters that we look at are in the Perseus arm that's cracking on for 10,000 light years away. But this galaxy, obviously this star cluster, is in between the two spiral arms. But it's not that clear. There's still some obscuring material in this gap in between the arms. Because if you look at the cluster, you can see the top half of the cluster is brighter than the bottom half, and the bottom half is not cloud this time, but it's gas and dust in between the spiral arms that is blocking the view. So it is absorbing some of the starlight from those stars there. So that's a very nice cluster indeed. We will look at, do you want to move it to, I don't suppose you can see the gas cloud that's near it, can you?
I could try with the other, if I change to, oops, a hydrogen alpha filter.
Yeah.
On this camera.
Yeah, or you could just the cluster needs to be at the top left of the screen for you to see the gas cloud that's near it.
Right. I can attempt to move the telescope.
Yeah, go for it.
In the right direction. So this needs to be up here.
Yeah, and you should see the gas cloud where that is now.
So what I'm going to do now is go for a fairly short exposure.
Yeah.
5 seconds.
And this gas cloud, if we can capture it through the haze, is in the Perseus arm, so it's more than double the distance. So now it's shortened the exposure, so we can only see a few of the bright stars in the Messier 52.
So that.
And then he's going to move it well up to the top left and then increase the exposure, and we should pick up a gas cloud.
The first thing you need to be sure of, because you're moving the right way. So I've given it a big jog now to move upwards, hopefully. Come on.
How long an exposure are you giving it?
5 seconds.
So it should change we should see the image refresh every 5 seconds. So
I can hear the mount moving. But,
we'll suddenly see the stars move. Come on. No, it's not happening. Do you want us to come back to you?
Yes. Okay. I'll put the cluster up there and I'll see if I can get.
Yeah, we'll come back to you. We'll go back to Paul now and see how he's getting on with his cloudy. Now we can see it's moving. The things are blurred as the telescope moves. But we'll go back to Paul, see how Paul's
I'm having awful trouble just at the moment with the
technology. All right, that doesn't worry. We don't mind.
Yeah,
we'll sort it out. And I suspect Mick is, as he hasn't moved, is still having problems. No doubt, give us a thumbs down.
Which is just 2.
Paul, if you're having problems, we'll just finish with the moon. We'll look at the craters Messier.
You want to get your?
Is it if it's not gone behind the tree yet?
No, it's well placed. I can go back there.
We'll just finish with the 2 craters Messier.
Okay, give me a moment. But what I'm having trouble that the auto guiding is failing because of the cloud, and so it's going and locking onto the wrong star and stuff.
Right.
The moon we might be able to find without any technology.
Oh, good, because Paul's got Paul's neighbour's got a dirty grey ash tree in his garden, and the moon is rapidly approaching the ash tree. So we're hoping to see the moon just before we have to finish. And the 2 craters we're hoping to show you are very small craters, but one of them is oval. So you can guess what has happened. An asteroid about 0.5 kilometre in diameter has come down at an incredibly low angle and hit the moon and then bounced and made the second crater. I can hear things whirring away, David, but
yeah,
nothing's moving.
That was me.
Oh, that's yours, is it?
Come on.
That's it. Talk to it. If all else fails, talk to it.
I think it's trying to stack the image or some such thing.
Right.
So it's.
Don't worry.
We'll get there in a moment.
But that's, as I say, a star cluster in between the spiral arms. And of course, the third spiral arm, which we won't see any of, is the one between us and the nucleus, the Sagittarius spiral arm. That's well seen in the southern hemisphere and where the center of our galaxy is. So they're the three main spiral arms of our galaxy, coming from the nucleus, where there's where you can see the bulge. If you're in Australia, they say the Milky Way is absolutely fabulous. It's much brighter than the Milky Way in the northern sky. So, but once you come away from the bulge, we've got the Sagittarius spiral arm, then the Orion arm where we live, and then the next arm going away from the nucleus is the Perseus arms, and that's where we'll see many star clusters, and later in the year we'll show you some more star clusters in the Perseus arm. It's just a question of waiting now to see whose telescope picks up the next object.
Yeah. I'm still sharing.
Yeah. I don't think Paul's there yet.
I did a go-to and it missed it by about 5 degrees.
So you're manually moving the telescope.
Yeah.
Those squares that you were looking at David's on David's screen were the size of the images he can produce. So if he wants to zoom in on something, he has a different arrangement of cameras. So you can have a different
telescope.
Sorry, and telescopes, yes. So you can see things at a different scale.
I'm deeply puzzled by this. I'm going to give you a good.
It's a bit difficult doing live, but when you're on your own, you can switch it off, go and have a cup of tea, and come back later, can't you?
Yeah.
Right.
Okay. Paul's nearly there, so if you want to stop sharing, we'll come back to Paul. Right, did you find the moon?
I don't know yet. It's awfully bright.
Yeah. Here it comes. Right, we're back on, that looks like Copernicus again, and Kepler.
That's what I aimed at.
That's good.
Got to sort the focus out, because focus turns out to be different for the moon. You wouldn't believe it, but it is.
I'm not going to say a silly thing like, oh, it's closer.
Yeah.
Anyway.
Hold on 1 second while we...
No, just sharpen it up. We'll see what happens.
That's better, isn't it?
Yeah, it's coming sharper. It's going the other way now, isn't it?
That might be as good as it gets.
Yeah, because it's still fairly low down in the sky.
It's directly over my neighbour's chimney pots, so there's probably a lot of heat rising.
Yeah, we can see it shimmering a little bit. So that's heat haze from the house causing that. That's why stars twinkle. It's the atmosphere causing the stars to twinkle. So while twinkling stars are good for poets, it's not good for astronomers. Right. Do you want to?
Yeah. So where are we heading?
If you go to the other side of the moon.
Oh.
So you should.
Asking.
Yeah, you should.
Is it this way?
Go on, move. I didn't see which way it went. Go on. Yeah, that's the way. Keep going.
You know, I got it right first time.
Right. That's it. We're nearly there.
That's the Apollo 11 landing site.
Yes. Do you want to point to it with your cursor, or have you moved on? No, we can see it.
I think it's just about here. Is this correct?
That little crater there is called Moltke, and that's about 3 kilometers in diameter. And just coming down and slightly to the right is where the Apollo 11 astronauts landed, about there.
There.
Yeah. So they chose that area, the lava-filled basin, the Sea of Tranquility, because it was obviously flat and very few craters, whereas the lighter areas of the moon are where it's hilly and often heavily cratered. And then carry on.
Nearly there.
Yeah. And now we're coming to the edge of the moon, and you can see it's just a little bit past full because we're seeing some detail, and we're seeing shadows. Right, now I think you have to bring the image down so we can.
This is Messier here.
There we are. Yeah, we can see the two craters.
Yeah.
And they're about 10 kilometers apart, and that's where the meteorite or asteroid hit and bounced. It was coming in from the left-hand side of the screen at an angle, and the left-hand crater is the oval one. It's about
Oops, too much.
no, that's okay. And I think we can even see the ejector that came out. That's all right. Just bring it back up. Yes, we can. It's very near where your cursor is.
Yeah, I'm just trying to get it dead center for you.
Okay, thanks.
There we go. That should be right.
Let it focus. And because the asteroid came in at such a low angle, the stuff that came out of the second crater when it made the impact is very directional indeed. And Paul will whiz over it with his cursor once things have settled down.
All coming out this way.
That way, yeah. It's over.
Just try and tweak the focus for you.
Okay, Ta.
Very sensitive.
Yeah. That's good. We can see the two. No, it's just gone again. And some of it's due to turbulence, isn't it, in the atmosphere?
Well, you can see how much it's dancing around.
Yeah. We just have to wait for the good image to come along. Because sometimes the craters almost disappear because of the atmosphere.
There's actually a small cloud in front of the moon now as well.
Oh, joy.
That's why it's doing so much turbulence.
Yeah. But we can see the ejector as a faint stripe going off to the right and up at a slight angle. That's that was a good.
That was nearly good, wasn't it?
Yeah, that was a good frame. So that's how we know that the asteroid came in at such a lot from the opposite direction. So that's good. So I think what we're going to do, as we're a telescope down,
I can show you something.
Go on then. We'll just go back to David to finish off. What have you got?
I have an interesting object here. You can tell us what it is.
Oh, thanks. Put me on the spot. Why don't you?
Absolutely. Share screen. I believe I'm on 7538. This little thing here. Is this what you were hoping to see? This is an H-alpha image.
Yes, the near the cluster.
Near the cluster.
Yeah, is that it? Yeah, that's it. That's brilliant. And this is a gas cloud that is not too far away from Messier 52. And it's called the Bubble Nebula, of all things. And we can't quite see the bubble because the bubble is just there. That's it. We can see a slight brightening.
Yes.
But that's the molecular cloud, this cloud of hydrogen, and just where you had your cursor, just there is a bubble, is a perfect bubble, and it's caused by a massive central hot star that's blowing out stellar winds, and the winds are pushing against the interstellar gas, a bit like a snowplow, and sweeping it up into this perfect bubble. We'll perhaps have a go at this again when we've got rid of the high level cloud on another week. And
There
this,
it is there.
yeah. And the cluster is just off the screen at top left. Oh, this is in colour. We can see the distinctive red colour of the hydrogen gas cloud, and
there it is.
Yeah, and the bubble is where that little point of light is. If you that one, that is the star that's created this bubble, and also exciting the gas so it glows. But the strange thing is the bubble or the star is not in the center of the bubble. That's because of different densities in the interstellar medium. And the stellar wind is moving fairly rapidly at about 7 million kilometers an hour. So it's gradually making the bubble bigger, and it's a fairly massive young star. Okay.
Is that it there?
The molecular cloud.
Yeah.
Yeah. It goes to the left is much fainter,
Yes,
but the
there.
brighter portion is around the star that's created the bubble.
There it is.
But the bubble is probably about just a bit bigger than the size of your cursor. We can't quite see it, so
it's there.
Yeah. But we'll have another go when we've got perfectly clear skies. So it's time for us to stop. And again, we've had a few difficulties, but we get over them. That's good. And I'll hand you back to Matt. Over to you, Matt.
Wonderful, thanks, guys. Very, very interesting as always. Thanks for making making the best of some clouds.
Yeah. Thanks to Paul, David, and Mick. Sorry, Mick's had trouble with his cloud.
It's completely cloudy here now. I can't even see anything. So it's amazing how quickly it's changed.
Sounds like we timed it perfectly.
Good. Okay.
Wonderful. Well, thanks very much, guys. And thanks to you, Brian, for doing the commentary, and to Hayley as well for being our speaker. We will see you next Wednesday, same time.
Good night.
Right.
There we go.
Well.